What's up, guys? It's your boy Neil. We are back with another video. Second video of the channel. It's good to be back. Here I'm explaining this problem. There's a jet and it's trying to slow down, and so it's deployed these vanes. And essentially, it's supposed to slow the jet down. And so, how does this generate thrust? Well, there's mass flowing in, and that mass flows in at a certain speed, and it flows out at a different speed. And so for that change in speed to happen, there has to be some sort of force involved. And the way force is related to mass flow is that force is equal to mass flow times the speed in, or the velocity in minus the velocity out. Now, here they're asking for the fraction n of the engine thrust. So the braking thrust as a fraction of the engine thrust without the vanes. So for that, we need to know the braking thrust and the engine thrust. And so how are we going to calculate thrust? We're going to calculate it using this formula. We have 50 kilograms of air coming in, and we have 0.65 kilograms of fuel as well. So the fuel, so the air, we know that it's coming in at 200 kilometers per hour relative to the nozzle, and it's leaving at 650 meters per second relative to the nozzle. But the fuel, since it begins inside the plane, I'm going to assume that it starts in the plane at a velocity of 0, and then it leaves the plane with a speed of 650 meters per second. Essentially the same speed as the air. So there's that. And you can see that the air is leaving in this direction and in this direction. But since it's symmetrical, we can just assume that the vertical thrusts cancel, because this speed is going to have a vertical thrust this way, and then this speed is going to have a vertical thrust this way, but the thrusts will cancel, and so you only end up with a thrust that a thrust that way. So that's how we're going to solve it. So let's start. So first we're going to, since the fuel and the air both contribute to the engine thrust and the braking thrust, we're going to have to calculate each of those separately. So we're going to start with the braking thrust. And we're going to calculate that using this. So let's start with the air. The air starts at a speed of 650 meters. No. It starts at a speed of 200 kilometers per hour, which is 55.56 meters per second. And then it leaves the engine at a speed of 650 meters per second at an angle of 30 degrees. So since the vertical components cancel out, we're only going to consider the component of the outward speed in this direction. So V in is 55.56. And now it's important to define positive and negative. So I'm going to start by defining positive x as this. And so the velocity in, since it's coming in this way, it's negative. Now the velocity out is 650 times sine 30, which is 325 meters per second. I'm just gonna verify that because I don't trust my mental math. Yeah, okay. So next, we need the mass flow rate, and the mass flow rate is given as 50 kilograms per second. So the thrust due to the air is 50 times Vn, which is negative 55.56, minus V out, which is 325. And so that should be equal to 19,028 newtons. Now we need to calculate the thrust due to the fuel. So the fuel starts off at a speed of 0, and then it's accelerated to the same speed as the exhaust gases. And so Vn is 0, V out is 325 meters per second, and the mass flow rate, as given in the problem, is 0.65 kilograms of fuel per second. Now the thrust due to the fuel is going to be 0.65 times Vn, which is 0, minus V out, which is 325 meters per second, which is going to be, oh wait, this is actually negative over there. Negative to 11.25 newtons. So the braking thrust is just going to be the sum of both of those, which is 194. Okay. Oh, wait, no. I put that in my calculator wrong. It is 190 degree. Which is 9239.25. Now we're going to do the same thing for the engine thrust. So the engine, these vanes, I'm going to assume that they're only deflecting the air, and they're not actually changing the speed. They're only changing the direction. And the reason that I'm going to do that is partly because I'm going to assume that there's like no friction here and the air like sort of doesn't slow down. And it's also because they just don't give us the speed of the air when it's leaving with no vanes. And so, yeah, so usually this speed right here would be pretty much greater than or equal to this speed right here. So I'm going to assume that it's leaving at 650 meters per second. So we're going to look at the air first. We have mass flow rate is 50 kilograms per second. We have the speed in, velocity in, is 55.56 meters per second. And we have the velocity out as 650 meters per second. So the thrust is going to be equal to 50 times 55.56. Now the velocity in is negative and the velocity out is also negative, and so this is negative but this is positive because it's subtracting a negative number, and we get these many newtons. And then for the fuel, we have the mass flow rate is 0.65 kilograms per second. The speed in is 0, and the speed out is negative 650 kilograms per second. So the thrust is just going to be 0.65 times 0 minus 650, which is 0.65 times 650, which is 422.5 newtons. So the fraction n, I'm just going to assume that they didn't care about the sign of it, would be this over the sum of these two. So first I'm just going to calculate net engine thrust, which would be 422.5 plus 29722 newtons, which is, and so N would be net braking thrust over net engine thrust, which is 19239 over 301, which should be 0.638, which is the right, should be the answer. Yep, and it is the right answer. So there you go. Hope this explanation made sense, and hope I will see you in the next video.